Okay, let's see here. All right, so let's get started here. So we have a question from the optimization, or yes, 4.4, number 58. Okay, so let's start with that. So that one is the one that looks like this. All right, so more or less like that. It says the arbellos is the region enclosed by three mutually tangent circles. So that what that means is they intersect that right exactly one point, and the tangent or the arbellos is the area, the shaded area of that portion. Okay, so it says given an arbellos in which the diameter of the largest circle is 1, so from here to here is 1. Okay, it says what is the position of point B? So let's say we have A, B, C. So we're looking for the position of point B to maximize the area. Okay. Okay, so let's see what we have here. So let's say that I call this here. All right, we'll call that the diameter of this smaller circle here. So if I do that, that means the diameter from here to here would be 1 minus x. All right, so that'll include everything from here has to add up to 1. So when I add both of those, that should be equal to 1. Okay. All right, so then the area of a semicircle with diameter d. So keep in mind that area is pi r squared. Okay, or at least here, half of that. Okay, so that's the area of a semicircle. All right, now if we know that, we know that 2r is d, or r is d over 2. Okay, so using that, okay, all right, so we know that, and let me plug this in here. So the area would be pi which reduces to pi d squared over it. All right. So what we have so far is the area of a semicircle with diameter d. So now, so far I haven't done anything. All I've had is just presented the area here. So if I want to find the area of the shaded region, right, we can think of the total area, which is half the circle of diameter 1. So A so the big or biggest semicircle, the area of that would be pi over 8. Okay. All right, so now let's take a look at the area of these smaller ones. All right, now the area of this small one would be the circle from AB. That would be pi x squared over 8. All right, and then the circle with diameter from BC, the area of that would be pi 1 minus x squared all over 8. Okay, so now in order to get the shaded area, I'll take the large area. So now we can have our function here, a of x, pi over 8, the big one, minus both of these small ones, pi over 8 x squared minus pi over 8 1 minus x squared. Okay. All right, and now we have our area function. Now we have a function in terms of x, and let me do some simplifying here. All right, I'm going to factor out the pi over 8. Okay, and then I can go further, right? I have that. Let me distribute this and then combine like terms. Okay, here, doing that, we'll have the ones cancel out. The ones will cancel out, and I'll have 2x minus 2x squared, or okay, so I haven't done anything yet. All I've done is simplified my area function. So now this is what my area function is. All right. Okay. All right, so now let's maximize this function here. So let me, I'm going to move to a new piece of paper here. Okay, so here it's important to realize that we have this right here. It's between 0 and 1. We're bounded by that large outer circle. So if I find the derivative here, we'll get pi over 4. 1 minus x plus x. The derivative of that is negative 1, which simplifies to that, and that the critical point of this is when x is equal to 1/2. All right. Okay, now what does that mean? That means that in terms of my Arbelos, in order to maximize the area, I should have a 1/2 by 1/2 tangent semicircles here. When that occurs, we get a maximum shaded area there. All right, notice that in this case, the endpoints result in an area of 0. So that would mean that we don't really have an Arbelos. We just have one of these completely overlapping the larger semicircle. So the only way that we get a max shaded area is when x is equal to 1/2. All right. Any questions? Is this clear? Can I explain something further? Would you like to see the other sheet as well? All right, can I answer another question then? No, that's it. Again, use the sidebar. On the side there, there's a nice chat bar. You can post your questions there. All right, all right. So Grant's looking for one. Anyone else can feel free to jump in and post one on the side. All right, so here we go. We got one. So Grant has 25 on 4.4. Okay, so let's take a look at that one. Okay, 25, 4.4. Okay, so let's see. A rectangle is constructed with its base on the diameter of a semicircle with radius 5 and with its two other vertices on the semicircle. What are the dimensions of the rectangle with maximum area? So let's take a look at semicircle. We'll think of this thing right here, right above the x-axis. And it says that it has, with a radius 5. So if this is our origin, this would be 5 and negative 5, right? So our equation here for the constraint, right, if we think of the equation of the circle, would be right, will be something like this. Equation of a semicircle with radius 5. All right, and then solving for y, I just need the top half. All right, so just knowing that I only need the top half, all right, I'll use the positive value for the square root. Okay, so we have this so far, and the way I'm going to construct my rectangle is like that. Okay. All right, so I want to maximize the dimensions of max area. So again, if we think of area of a rectangle is length times width, so this is y. So the area is 2x times y. All right. Okay, so we have that, and now again the point here is xy, but now I have a constraint here for my y. I can do here times y x squared. Okay, and now we have an area. We have an area function in terms of x, right? In terms of one variable. So I'm going to go ahead. Once I have that, I'm going to maximize this equation here. All right, and notice here for the parameters, or sorry, not the parameters, the domain of this function. Right, it'll run, well, we can include the endpoints, right? But the endpoints, realize that that's not a rectangle, it's more like just a line, right? When x is 0, that corresponds to just a rectangle of width 0, which is not very useful for our application. And when x is 5, right, that corresponds to 1 with the length of 0 here. So this is just a line there. So the max would have to occur somewhere in this interval. So I'll try to find it by taking the derivative, right, a prime of x. So to do that, take the derivative of this, which is 2. Leave the other function alone. And now 2x, the derivative, leave that one alone. The derivative of this would be 1/2 power rule, 25 minus x squared to the negative 1/2, and then don't forget the chain rule, times the negative 2x. All right, so now let me clean things up a little bit here. So here we'll have 2. All right, on this side we'll have that 2 will cancel, but we'll still have another 2 here. So we'll have negative 2x squared. All right. Okay, so we'll have something like this, and now at this point we realize that we have to set it equal to 0 and solve. Now when you have at least one of them is a rational function, or it has the denominator includes a value of x, think of writing it as one fraction, right? So at this point, right, so I want to write it as one fraction. So common denominator is going to be this, so I'm going to multiply here by root . Right, I'm going to multiply by that root. Now doing that, here, now I'm going to take a couple of steps here. I'm going to factor out that 2. And now I'm going to write everything under one fraction. Okay, so keep in mind that 2 is out here, right? So I took it out of this one and that one right there. Okay, so taking that out, now we'll see we have over here minus 2x squared. All right. All right, so now once we're here, we can have here we'll have that. And again, once we're at this point, we have to remember what we're looking for is when is that true. So I'll set my equal to 0. Right, so when does that equal to 0? And again, here, we won't worry about the denominator in the sense that I know that 5 makes that 0, but I know I don't want to include my endpoints. It's not a useful data point. What is going to be useful, what is going to make this 0, is when this part of the fraction is 0. So if I do that, I'll solve for x squared, and we'll get 25 over 3. Taking the square root, we'll get x is 5 over root 3. Okay, and they ask us for what are the dimensions. Okay, so I have the x value for the dimensions. That is that. Let me zoom out a little here. Okay, so now what about the y? To get the y, right, keep in mind y is equal to 25 minus x squared. 25 minus thirds. Let's see, what do we get here? All right, so in this case we get, which simplifies to 5 root 2 thirds. All right, and those will be my dimensions. This will be my y, and actually the x, so would be 10 over root 3. Since there are 2 x would be along the length and 1 y along the way. Okay. Any questions on this? I know the work is kind of all over the place. I try to squeeze it in there, but I think if there's anything you'd like me to go over on this one, please let me know. Okay. Yeah, you're right, Tom. I just saw that right now. I put the 2 out here, so that is gonna. So correct. I factor out that 2, so I shouldn't have put that 2 there. The 2 should definitely go here and here, which means that on this point, all right, we should get that. All right, so sorry. Let me back that up. I miswrote that. That should have been just a minus x squared, which means that the next one should be minus 2x squared. All right, and now moving forward, this should be minus 2x squared here. So our x value would be 5 over root 2, which means the dimensions when I double it would be 10 over root 2. Right, and over here, when we have 25 halves, that'll be 50 halves. We have 25 or 5 over root 2 for my y. All right, yeah. Sorry about that. There should be, you're right. That 2 shouldn't have been there here. So that changes our answer a little bit there. Okay. All right. Any other questions on this one? I have 2 requests for number 17 on this section, so I'll do that next. Alrighty then, let's look at the next one then. So the next one, we're still on 4.4. We're going to do number 17 now. Okay, so shipping crates. Here it says a square-based box-shaped shipping crate is designed to have a volume of 16 cubic feet. The material used to make the base costs twice as much per square foot as the material in the sides, and the material used to make the top cost half as much. What are the dimensions of the crate that minimize the cost of materials? Okay, so let's see. This is a good problem here. So we have right, if we think of a box, right, so what we're after is we have a square base. So what we can say is that here, S and S, we'll call that the base. All right, it's square, the sides are the same, and some length L. Right, so I know in this case for my particular box where the base is squared, the volume is L times S squared. And I know that in this, for my problem, they wanted to stay at 16 cubic feet. All right. And now we want to think of here, we want to minimize cost of materials. All right. Now, notice when they say this, minimize the cost of the materials, what that means in terms of the application is we're looking at the surface area. All right. Think of if we want to make this box, we want this material, and then the material to make all of the sides. So 6 different sides. The only thing here, there's one thing is that the base, which will say the bottom here, S squared, that's the area of the base. Cost of materials, or in this case, surface area. All right. So we need to come up with our cost function, which if let's say that they don't tell us what the exact cost is, but we know we have a comparison between the two, right? So the base costs twice as much as the sides and top. All right, so let's say C be the cost of the sides and top, which means that 2C would be the cost of the base. All right, and we'll assume that C is the cost per square foot. Okay, so that is what's known so far. So that means if I want to come up with a function here, so for our cost function, the cost to produce the base is going to be 2C, or actually it'll be in, let me leave off the variable for now. The cost for the base would be the area times the cost of the material. Okay, so here we have area times cost of material. Okay, so this is just for the base here. Now the top is also S squared, but that's made of a different material, right? Different, and it costs half as much. So now that would be C times S squared. Oh, sorry. 1/2. I didn't read that all the way through. Right? C is the cost of the sides, and 1/2 C is the cost of the top. All right, excuse me. There's three different materials here. Okay. So far that's what we have, right? So this here is the cost to make the base, the bottom, the top. The material's cheaper, and now the four sides that go around it. That area is S times L, and the cost for that is just C. All right, and there are four of those. Okay, so again here, cost for the base, cost of the top, and here, cost of the four sides. Okay, now keep in mind, it looks like we have three variables, but we only really have two. C is a fixed constant. All right. I don't know the exact price, but I do know that it is a fixed constant. It's not variable in our problem here. All right. So we're okay so far. Is this should I slow down and explain anything further, or can we move on here? All right. All right. If there's no question, if everyone's good, I'm going to keep going from here. Okay. So now we only have two variables here. Those variables are the dimensions of the box, right? The S and the L. So I need to get rid of one of these, and the L in particular, right? So the way I'll do that is, all right, let me just scroll back up here. If this is true, right, that means that L has to be 16 over S squared. Okay, so I'm going to use that fact to substitute into my equation. Okay. And now I have a function in terms of one variable, right? And that variable being S. Okay? So let me simplify this a little bit. I'm going to factor out a C, and we'll have that. So all I did was factor out a C and then multiply it here. And I'm going to do one more step. These are like terms. 2 plus 1/2. We have 5/2. Okay, so we're here with our cost function with respect to the side S. And now let me minimize that. All right, so I'll minimize it by taking the derivative with respect to S. Doing that, we get 5S. The 2's cancel out here. Here I'll have minus 64 over S squared. All right, so now we're almost there, right? So we got a lot of work here, but we're almost at the end here. Now I need to find out, when is this true? Okay, so I'll look at this. Right? And in fact, we can divide that C out. I know it's a constant bigger than 0. Okay, so now we're good solving this problem. Right. What's good to note here is that the actual cost looks like it didn't come into play, but what actually came into play was not so much the cost itself, but the ratio in the cost of the sides, right? Twice as much, half as much to the sides. And that played into how we got these numbers here. All right. So the cost itself wasn't really a factor because we already saw how it was related to the other cost, the top and the bottom. All right. So here, let me write it in under 1. Sorry, that's S squared. Okay, so if I write this with a common denominator of S squared, that means here I multiply by that. All right, and that'll give me this function. And again, we have critical points for our derivative when S equals 0. But again, this is not very useful. I don't want a side of 0, right? That would not be a very efficient or effective box. So then I need here, I need to solve that, and that gives me S cubed equals to 64 over 5, or the side would be cube root of 5, 4. All right. So that gives me the dimensions of the base. To get the L, remember that's 16 over S squared. All right. To get something like that, you just plug that in here, but I won't do that here. I'll let you guys finish that problem up. Okay. Any questions on this one? Can I explain something further, or we're okay with the results here? Okay. So if there's no other questions, can I do another one? Well, Tom, what can I explain as to what I did to convince you? No, it's good. Okay. I think here it is very involved. I will agree. The involved came with the costs were different for all 3 of the sides. All right. If let's say I asked you if the material was all the same, then we should be able to do something like that, right? That would just be a simple, or not simple, a surface area one. Right? I like all of these, Emmanuel. That's why I assigned them. I think you guys picked the ones that I really like. That rectangle area under a curve, I like that a lot. 4.2, all right, there we go. 4.2, number 71. Okay, so let's do that next. All right. right, so let's see. Let's look at 4.2, number 71. Okay, so this one says that every second counts. So you must get from a point P on the straight shore of a lake to a stranded swimmer. All right, so let me draw the picture here. So something like this. So you say here, we'll call that QP. This is the shore. Now we have some. Okay. Am I looking at the right? Oh no, sorry, that was 4.1. I apologize. That is not the right one. 4.2, number 7. Okay, so here. All right, so now I got the right one. Number 71 is here. Okay. All right, that's better, right? And here they want me to use the second derivative test to find. All right. Okay, so for this one, we'll find first our first derivative. Doing that, we get 3x squared minus sine of x. All right, and then here, all right. Okay, now for this one here, what we have to do is, so the first part at least, we have to find when is this true. All right. Now the first one, well, one of them should be really straightforward, right? In the sense that if I look at that, if I let x equal to 0, right, that is a critical point. All right. All right, that came kind of just from inspection, just kind of looking at this function. I said, all right, 0 is going to work. Now, as far as how to find here, so f double prime of 0, we'll get a -1. So my second derivative at 0 is negative, which means that I have here a local max at x equals to 0. All right. Now the trouble here is, how do I get the other one, right? And we know it exists mainly because if I draw a graph here, all right. All right, so if we see that, and actually it's hard to tell. Let me zoom more. All right. So we could see it there, right? It's hard to tell. For something as the second one, when it has that little t, it's asking us to use technology, and we can use our graphing calculator or Desmos to figure out what the other one is, right? And if we do that, actually, get a we could see that we're going to get the other zero when it's approximately 0.327. All right. Okay, or we can do what we did today in our Tuesday class. We can actually, now we can use Newton's method or something like that if we wanted to find the roots for that one. But anyways, that's neither here nor there. We found the root, and now we can take the second derivative and plug in 0.327. Right, and if you do that, what we'll find is that it's greater than 0, which means that we have a local min at. Okay. All right. All right. Does that answer your question, Ismael? When you see those T, it's encouraging you. It's asking you to use some kind of technology. All right. Okay. So let's. If there's no questions here, let's see. I did 71. Let's do 4.3. Oh, okay. All right. How about so Emmanuel, I'll answer that first one. 4.3, number 50. Okay. All right, so 4.3, number 50. So it states that the function has 3 real zeros. And exactly 2 local minima. All right. All right. So if we think of what this could possibly look like, all right. That's my ruler here. All right. So something like this. Again, the actual value of the zeros is unimportant. I just know that at 3 instances, exactly 3, it crosses the x-axis. All right, and I wanted to have exactly 2 local minimum. So if I think of here, so okay, let's start off. It probably comes down this way. So this is a possible example here, and then it goes up here. All right, but what if it did something like that? So maybe it had some kind of double root at the middle root here, right? And now when I look at this, it satisfies both of those conditions, right? has it 3 real zeros, 1, 2, 3, and exactly 2 local minima, right? This one and that one. All right, and these don't necessarily have to be the exact same. They look like they're the same, but it could do, right, several different things, right? It could maybe do, it could do something like that, perhaps, right? And that still satisfies the requirement that it has 3 zeros and only 2 local minima, which it does here. Okay. All right. I think here the part that that was probably how do I get that 2 local minimum without, you might want to go through it and then come back, but that wouldn't satisfy the 3 local minimum, or sorry, 2 local minimum. All right. Any questions on this one? I think so. What do we have on deck? Dewey Manuals 4.4 number 22, and then 4.9 number 77. All right. So let's do that. All right, so let's see. 4.4, number 22. So it says a 10-foot tall fence runs along parallel to the wall of a house at a distance of 4 feet. Okay, so it looks something like this. Find the length of the shortest ladder that extends from the ground over the fence to the house. So I'll call this L. That's my ladder. All right, and I want to minimize that value. Okay, so we have that. So it looks like we have a few unknowns here. We'll call that X. And then here, we'll call that H. All right, so now again, they make that assumption here. We have a right triangle. So we have square. All right, so now we have, a problem here in the sense that we have too many variables here, right? The L and the X are a variable, and even we have this H thrown in here. So we have to realize that we have a similar triangle here, right? If we think of this angle, whatever we want to call it, but the triangle here, the smaller one, and the bigger one are similar, right? Which means that if I think of the ratio of the sides, h over x plus 4, that should be similar to 10 over x. All right. And that implies here that now we have okay. All right, so now let's do this here. Let's substitute in here L squared equals to all right, and now we have our function here. Now, one thing to realize here is this length of L, the ladder here. So when I find the derivative, I only have to minimize L. Right, they're both positive values, so the function itself, these are two equivalent statements here, right? So what I mean by that is if I wanna optimize this function, I can call it, I can define L squared to just be equal to my function f of x, which is this one here. Okay, and I'll find the derivative of f. All right, so doing that, all right, we'll start with this function. Leave the inside alone. Now I'll leave the other one alone and take the derivative here. All right, and we get this value right here. So that means that here we'll have x cubed. All right. All right, so far we have that as our derivative. All right, so now it's gonna get a little messy. All right, so let's try to simplify this, right? So I want to simplify this. So I'm going to rewrite this all over x cubed. So doing that, that will give me okay. All right, so it's not as bad actually, because now what we see is going to happen, let me, that will simplify. And these two have a factor of 2. So let me take that out here. All right, so now we have that as our function here. Okay. All right, and now let's figure out when is that equal to 0. All right, or the critical points. And what we'll see here, one of them is x is -4. But again, let's think of it in terms of my application, and it wouldn't make sense to be -4 feet away from the wall here, right? Unless we're on that side, in which case it's not relevant to this application. So I can get rid of that one. The only other possibility, or actually another possible critical point would be when x is equal to 0, right, when it's undefined. But again, that also doesn't make sense in terms of having it here, right, our ladder to be completely vertical. So that one doesn't make sense either. So the only other outcome and if we plug that in, or just to get an approximation, it's about, the ladder should be 7.3 feet from the wall. All right. And we can confirm that's a local min. We could plug it in into our F, and we'll see we'll get a local minimum. Okay. All right. Any questions on this example here? All right. Okay, so let's see. If there's no questions on this one, let me. So I got through that one. We have 4.9, number 77. I told you, Emmanuel. I really like those the areas on there, a curve and surface areas. And those are all good problems. Tom, we haven't gone over that yet. Can I lead off our Tuesday's discussion, actually solving that and getting into how to approach those type of problems? All right. I think for the exam, we should focus on just finding the antiderivatives. Those applications we can push back to the next chapter and so forth. Is that all right? All right. Well, can I answer any other questions? Oh, okay. How did I go from L squared to f of x? So in this case, all I realized was that minimizing something like this, right, is the same as minimizing L, right? So there was no need really to do a derivative. This is the derivative that I'm finding. So I just renamed L squared to be my function f of x, which is the one that I'm minimizing here. You could have just figured out, you could have just thought of it like this. What really I'm trying to get at is that we don't need to use the power rule. I want to equate the problem of taking the derivative, or sorry, minimizing L squared is the same as minimizing L. So I don't want to worry about this stuff right here. I can just take the derivative with respect of L squared with respect to x. The important part here was having this function and taking the derivative of that with respect to L. And let's not let the L squared kind of get in the way of doing that. So I just renamed L squared to be a function with respect to x, which is how I want to treat it. Right? I don't necessarily want to apply the power rule here. I just want to minimize L squared, and that's the same as minimizing L, the length of the ladder. Okay, does that make a little sense, Grant? Okay. Yeah, and the thing for that, there's another problem when I did this section that I did the same kind of thing, and mainly because the reason for that is just we're looking at this problem, and the value of L squared itself, at this point, I have a function in terms of x, and I want to put my attention to that. So I'll just say, all right, I'm going to get back to this L squared later, or to the L in general later. Once I find my x, I can go back to the original here at that point to plug in. All right. Do 61 and 4.3. With the graphing utility. All right, so let's see here. Okay, so here for this one, they want us to use analytical methods together with a graphing utility to graph the following functions on the interval from negative 2 pi to pi. So again, it's undefined at x equals to 0. All right. So it is in all right. We can also see it's an even function. Right? Remember cosine. All right, so then that and that is even, right? The squared part. So now let's take a look at what our analytical methods tell us. Okay. So here, I'm not. How is it even? Okay. Yes, cosine is cubed, but it's even because the cosine function is of negative x equals cosine of x. All right, regardless of what power, even if it was the first power, second power, that doesn't matter, right? It's not a polynomial, right? That would tell us something different. But the fact that this is true, right? If you remember the cosine function, that's an even function. It's symmetrical about the y-axis. So the fact that I cube it doesn't really give into effect that it's even or not. Remember, the test for even or oddness is this. So now we have that's just cosine of x cubed over x squared. All right, so we have in fact an even function. Okay, does that make sense, Emmanuel? Okay, all right, so now here I won't do all of it. Well, I won't go through, I'll go through the process of how you would do something like this. Mainly because at this point here, I don't have it'll take a while. It's a little involved here. You'd use I would use a Desmos here. Okay. Uh, and what I would do is I'd find the derivative, right? And you can set that and really focus on this interval here, right? Find f prime, right, and see if it has any critical points. All right. All right, and from there, use Desmos to graph the derivative, and you'll see that it'll be a decreasing function on 0 to 2 pi. All right, and then use that fact here for f double prime. All right, and then right, and in fact, what you'll see is that the function does something like this. Right, where it has these kind of oscillations that aren't clear from this function here. All right, so just find these derivatives and graph the derivatives on Desmos so you can see that there's no, or at least the first one, there's no roots in 0 to 2 pi, which means it's always decreasing and there's no local max or min. But it does have some inflection points, which you can see are these things here. All right. All right. And you can find those using the root. You can just use the root finder on Desmos, where you just click on the point to give you those exact roots there, or approximate roots. You won't have the exact value there. Okay. All right. Why don't we call it a day here today? I'll post this online. I'll send the link out to where it is. And for those of you on the Tuesday, Thursday, we can do this again next week. Maybe on Monday. If it's Monday, I'll send you guys an email or I'll send out a tweet as to what time that would be. Okay? All right. Why don't you guys have a good evening and thank you for joining me.